All right, so we are now starting chapter 11. It's going to look similar to 8 and 9. We will be doing tests. We will be writing out a hypothesis, doing a test, coming up with a conclusion. And chapter 13 will also look similar, but we are not doing confidence intervals per se or doing hypothesis testing. We are doing a different kind of testing. They'll just look similar in that there'll be lots of calculations and then we will write a conclusion at the end. So you should have your 11-1 notes with you. And also, along with these notes, at the very end of the notes, there's a new table. And this is the chi-squared table. And so this should be on the last page of your notes. But we don't need it right now. Right now, we'll just start with 11-1, goodness of fit. And so we are going to be looking in this section at sample data consisting of observed frequencies. And we're going to see this in a row or column. And we're going to use a hypothesis test. However, we are not using the same table as hypothesis testing because we're going to be using different variables. But this is still, this test, a goodness of fit test, is still a hypothesis test. And so we have some notation. Capital O represents the observed frequency, observed for O. Capital E represents the expected frequency, so capital E. And then we have K, which is the total number of categories. So we haven't used K before. K is very common in math to represent the number of categories. We're going to see this again in chapter 13. And then, of course, N, the total number of things we're talking about, in this case, the number of trials. So going back to O and E, O is what we observe, and E is what we expect. So if I roll a die with the numbers 1 through 6 on it, I expect that I will roll each number. The probability would be 1 out of 6. So if I rolled them 6 times, I would expect that I would see each number once. If I rolled the die 12 times, I would expect that I would see each number twice. But that's not always what happens. And so I would say what I expect to happen, and then I would actually roll the die and tally how many times it's actually happening. So the observed is what's actually happening. The expected is what you could calculate based off the probability or, given the information in the problem. So like others, that has the requirements that the data are randomly selected. The sample data consists of frequency counts for each of the different categories. So like I was mentioning, we wouldn't just say there's 6 sides to a die. We would actually roll it and tally up and get that frequency. And then we would want at least 5. We've talked about this before. 5 is just a good number. Bigger than 5 is good. Less than 5 really isn't that many people or things to roll or whatever you're talking about. Okay, so our alternative and null hypotheses, they're still existing. They're just going to be written a little differently. And so the null is still equals whatever we expect. That would be the null alternative. And then the null hypothesis. And then the alternative would be going against what we expect. This will make a lot more sense when we do an actual problem. Okay, formula, test statistic. This time our test statistic is chi-squared. So it's pronounced chi. It looks like an X, but it's a Greek letter. And that goes to this table that you have at the back of your package, chi-square. And this is our chi-square distribution, which we'll use a little later. And then we have the critical values. And we will talk about how to use the table, the chi-square table, to calculate this. But one thing to note, I put it in bold, they're always right-tailed. These are all right-tailed tests. And you'll see that on the table as well when we get to the table. So we're going to use the degrees of freedom of K minus 1, and we'll talk about that again on the table. It's written out. And then finally, finding expected frequencies. So if it's not, sometimes it'll be given. What's the expected frequencies? And sometimes we have to calculate it. So if they're all equal, the formula is n over k to find the expected frequencies. If they are not equal, it'd be n times the probability for each specific event. So let's just look at those two formulas. I know I just said a lot of stuff. We're going to take this in baby steps. So let's just find some expected frequencies. So looking at example 1, we have a single die that is rolled 45 times. Assuming the die is fair and all outcomes are equally likely, find the expected frequency, which is E, for the empty cells. So they already rolled the die. They already told us how many times each number came up. We'll use those numbers in the future to come to some sort of conclusion. Right now, we're just trying to fill out the E row. And so, how many trials were there? The die was rolled 45 times. So they told us that in the problem. Number of categories. How many categories are there? Well, how many possible outcomes are there? So A is 6 categories. There are 6 possible outcomes. 1, 2, 3, 4, 5, 6 are the 6 sides of the die. And so these expected frequencies, well, it says all outcomes are equally likely, so they are assumed equal, which means we are going to use the formula E equals n over k. I know that because going back to the last page, it says if they're equal, E equals n over k. All right, so I'm using that formula. I already know n. I already know k. Put that in your calculator. Works out to 7.5. So to answer the question, all of these, since they're equal, they're all going to be 7.5. Now, the mathematical model is the exact, in a perfect world, what would happen? Well, 7.5 times we would get a 1. 7.5 times we would get a 2. But we're not rolling a half times. So really going to match up with the mathematical model. So it's okay to have decimals in the expected frequency. That's just, in this case, all outcomes are equally likely. If all things are equal, if I divide 45 up into 6 groups, each group gets 7.5. Okay. Now, what's reality say? Reality says that and I rolled a 2 6 times, and I rolled a 3 12 times. And so it's okay that our expected frequency, it's okay that we are expecting a decimal, because again, this is the exact mathematical model. This is not taking into consideration like reality of the actual data. Okay, similar problem, 45 times, but this time the die is loaded. That means they're not going to be equally likely. In fact, it says the outcome of 1 occurs half of the time, and the other 5 occur 10% of the time. So that's written out right here. The outcome of 1, 50%. The others, right there, they all have their 10%. Okay, get rid of that. And so we want to find the expected frequency. So how many trials are there? There's 45, just like before. How many categories are there? Well, technically there's 6, but it's really not applicable because these are not equal. And when they're not equal, we don't need to know what K is. Go back up to the last page. When they're not equal, we just need to know N, which is 45, and then the probability. And that was given. So we don't even need to know K. So yes, it's 6, but doesn't matter. What really matters in this problem is P equals either 0.5 or 0.1. So to calculate the expected frequencies, we need to do 2 because there's 2 probabilities. If there were 6 probabilities, I would have to do this 6 times. But I can just do it 2 times because the answers are the probabilities are either 50% or 10%. So the expected is n times p. And so there's 45 times 50% would be 22.5. All right, so for the others, there's still 45 is our n, a stellar number of trials, but the other ones only have a 10% chance of happening. So that would be 4.5. It's hard to see the decimal up here, but there's one in there. So for our expected frequency, 1 had a 50%, that would be 22.5. Half of our 45 we expect to be a number 1, because it's a weighted die. Other ones only occur 10% of the time. So all of these with 10%, again, I'm looking at 10% probability, all getting a 4.5. Okay, so for this next page, it's just a little picture to kind of explain what's happening. If our so this is our O, remember our O is our observed and our E's are expected. So if O's and E's are close, we are going to get a chi-squared over in the left hand, the empty space over here. Remember, these are right-tailed tests. So wherever is the red, that's our reject for the right tail, and whatever I'm coloring in blue right here is the failed to reject. So when O's and E's are close, the chi-squared is going to be in the blue, which means we will fail to reject the null. When the O's and E's are far apart, our chi-squared, I kind of wrote over it, but the chi-squared is over here in the red, and we are going to reject because it will fall into the reject region. So sometimes it's just nice to see a little graph of what's going on, but the bottom line is we are doing only right tail tests will be reject. And that's the same every time we have a right tail test, that's where the reject region is. So if you forget the whole, if the O's and E's are close or if the O's and E's are far apart, that's fine. That's not the super important part. The important part is to remember from before, the reject region on a right tail test is on the right side to reject. Okay, so, ooh, too fast. All right, so we're gonna do a whole problem here using the goodness of fit. So it says a random sample, 100 weights of Californians is obtained, and the last digit of those weights summarized below, just the last digit. We measure the weights rather than ask people to self-report. So if you ask someone what they weigh, they're probably going to say, oh, I weigh 200, or I weigh 210, 215, usually like those nice round numbers. Rarely people will say, I weigh 197, or I weigh 203. So a lot of times when we're rounding, it will end with a 0 or a 5. And even if we're not necessarily rounding on purpose, look at your driver's license. What did you put weight? Does it end with a 0 or a 5? Most likely it does. Samples from a population of weights which the last digits do not occur with the same frequency. And then it tells us if the original claim is false, all probabilities are the same. So just like before, the null hypothesis, all the probabilities are going to be the same. Now, that's not what I meant. What I meant to say is, just like before, the equal sign is going to be used with the null hypothesis. So if this one, they're all the same, I can just copy down what I see over there. Let me do black. Probability of 0 occurring is the same as the probability of 1, is the same as the probability of 2, it's the same as the probability of 3, and so forth until I get to 9. All of those digits, 0, 1, 2, 3, all the way up to 9, are all equally likely to occur. The alternative is going to be at least one is different. So at least one of the probabilities is different. And we want to say, oh no, I just messed up something. Here, make it bigger. At least one is different. We want to say at least one is different rather than they're all different, because if I wrote down this list, 1, 1, 1, 1, 1, you would say they're all the same. But if I did this and I changed that to a 2, you would say they're not all the same, but they're also not all different. There's a lot of ones, and at least one of them is different. The 2 is different, so they're no longer the same. So we just say at least one is different in order to take care of the fact that we have so many equal signs. You know, we have 9 equal signs, or 10, because we're talking about 10 things. I guess that would be 9 equal signs. Anyways, we will focus more on how to come up with that null and alternative in future examples. I just kind of want to go through the steps in this one just to show you the whole process. And so significance level, we always select alpha is 0.05. 5% is what we select when nothing is given. So a lot of similarities to chapter 9. And here we start seeing the differences in the calculations. So here is 0, 1, 2, and so forth. And then it gives us the observed. Now we're expecting that they're all equal. So we're expecting that they're all 10. I didn't even have to calculate it because it told me the first one was 10. However, if I did calculate it, I would say there was 100 people asked. There was 10 different choices, 0, you count it 1, 2, 3, 4. There's 10 of those. And so dividing that, I would get that E equals 10. But they gave us that E equals 10, so we didn't have to calculate it. All right, I'm going to do the first row, and then I'm going to give you a chance to pause and do these calculations, because it's important, as always, whenever we do something new, to do the calculations just to make sure you can them all in correctly. But this first row, we're just going to follow the rules at the top. Actually, let me back up a second. We are now on the first over this formula we're using right here in the box. Chi-squared is equal to the sum of the observed minus the expected squared divided by E. So it's broken down step by step in this table right here. We are going to take this last, add everything in this last column to get our total right here. But that we're kind of putting the cart before the horse. What we need to do first is fill out each step. So first row, 46 minus 10, because O minus E. 46 minus 10 equals 36. 1 minus 10 equals negative 9, and so forth. Next up, we're going to take that number and square it. 36 squared, 1,296 is positive 81, because negative 9 times negative 9 is a positive number, positive 81. All right, and then finally, let me get the circle out of the way so I have room. We are going to divide by E. So E in this problem was 10. 1296 divided by 10, 129.6. 81 divided by 10, 8.1. I love dividing by 10 because it is so easy to just move the decimal one place. All right, so what I want you to do is pause the video and fill out the rest of this table. And I am also going to pause the video. And when you come back, I will have all of those values filled in. So make sure you are pausing it now and that you are filling in that whole table so you have something to check when I come back. All right. All right. I'm back, and here are all the answers from the chart. Pause it again, double check all your answers. Notice the whole O minus E squared column is positive. Everything is positive because once you square it, it is positive. And then in dividing by 10, so I just move the decimal one place over. All right, so what I want to do now is I want to find the sum because that is what we are after. That will be our test statistic. So I'm going to take all these numbers and add them up. So go ahead and put all those in your calculator. Add all of those numbers. This isn't a fancy list. This isn't a quick shortcut. You literally just have to type all 10 numbers into your calculator. Plus, add them all up, and getting 212.8. So that is what is known as our test statistic. Our test statistic is always calculated by hand. Now this feels a little big, but we haven't done chi-squared before, so maybe it's huge, maybe it's not. But what we're going to do is now look at the table to find the critical value. So remember, n is 100. So since n is 100, we're going to take our degrees of freedom, which is 99. And I'm going to go over to this table, which is on the last page of your list. And we have the degrees of freedom. And remember, we had our alpha. So our alpha was given to us here. Oh my goodness. I did the hypothesis test and confidence interval degrees of freedom. Look at this chart right here. It's like it just knew I was going to make this mistake. So we have the confidence interval and hypothesis test was n-1. The goodness of fit is actually k-1. So let me go back and fix that mistake. We would have figured it out when our table didn't match our picture, but it should actually be how many categories were. So we said k was 10. So our degrees of freedom is 9. And we already said before our alpha was 0.05. So going to our table, degrees of freedom is 9. 0.05 is our alpha, and here it is, 16.919. Now these numbers are a lot bigger. Looking over here to the right, these get pretty big pretty fast, but they're still not 212 big. So 16.919 is going to be our critical value. And if you're looking ahead, you'll see it's click answers on it already. And so our critical value that comes from the table is always where our line is. And our test statistic, it's super big test statistic. It doesn't even fit on this, but this was calculated and calculated it, and we got 212.8. And so this is definitely in the rejecting of the null hypothesis. So we will oopsies, that was supposed to be a highlight. We will reject, I don't like that, I'm going to circle it. We will reject the null hypothesis. You can ignore this. The reason we are rejecting the null hypothesis is because the test statistic is in the critical region. Now, this is not a conclusion. This is a thought process. So you're not going to write this out when you're doing it. We did that whole thought process on the table. So you can either write it out, or you can just think it in your brain. But the actual conclusion, just like the previous chapters, we conclude there is sufficient evidence to support the claim and then remember, what we're supporting is the alternative, and the claim is that the digits do not occur with the same frequency. So going back, I'll scroll back to that in case you didn't write that down, but we are supporting, there is sufficient evidence to support the claim that the digits do not occur with the same frequency. So the null is that they're all equal. The alternative is that they're not the same, or at least one is different. So here is that last conclusion, in case you wanted to see it again. All right, one last problem for this section. And it says a doctor keeps track of the births that she delivers each season. She expects that the distribution will be uniform, because we always expect that it's going to be the same and the probability is all the same. But maybe they don't. So you could say the probabilities are each the same. But a faster way to write that would be, what was it? Right here. The births will have uniform distribution. That will be how you'll see it on the Newton Alta homework. The births have uniform, that means the same distribution. Don't say the births have the same uniform distribution, because uniform means same, so we don't need to be redundant. The births have uniform distribution, or the births do not have uniform distribution. So those are our null and alternative hypotheses. Sometimes it's just easier to say in words. So they're either the same or they are not the same. At least one is different. The only thing that you could do wrong really here is to say they're all different. The opposite of they are all different. The opposite of they are all the same is at least one is different. So it's better to say it's uniform or it's not uniform. Then this time we have a different alpha. So we were given alpha is 1%, so 0.01 significant level. Okay, this is a much smaller 4. So, and fill out this whole table. And then when you are done, come back and I will have the table filled out as well. All right, so at this point, these are the numbers you should have. Remember, to get O minus E, we're just subtracting. To get that final, or that second to last column, they should always be positive because we're squaring. And then what's happening is we're dividing everything by 30. So I kind of just rounded a little bit. It's gonna be a little clunky because those numbers go on forever. And I want to just give a little trick, a little shortcut for people that get fractions. If you don't understand fractions, if you hate fractions, feel free to ignore what I'm about to say and just do this the way that we've been doing it. But if you get fractions, I just want to say for a second, these are all, I'm basically adding up 4 fractions with a denominator of 30. And since I'm adding up 4 fractions with a denominator of 30, I could just add up the numerator and then do the division by 30 at the end. It plus the 36 plus the 2 4s and get 144. And then, or if you don't like that, what I just said, we already did the division. So just add 4 numbers that we already have in the final column. And you're going to get about 4.8. I think it's like 4.79999, all that. So we'll just say 4.8. So calculate, that's the one that we just calculated with our calculator. The next one, the critical value we're going to get from the table. So we have our degrees of freedom. I should write that out first. Degrees of freedom. What is our degrees of freedom? It's k minus 1. I know it's still early on, so it's easy to forget what K is, but K is how many categories are there? How many different answers could people have answered on the survey, or how many different times could these kids have been born, or whatever we're talking about? So there's 4. There's 4 categories. So the degrees of freedom, that's an equal sign. Oh, and that's a 4, goodness gracious. Okay, equals, no, actually it's a 3 because I do 4 minus 1. The degrees of freedom is 3. So going back to the chi-squared distribution table, we have our alpha is 0.01 and our degrees of freedom is 3. So we have 11.345 as our critical value. 11.345. All right, and I need a space picture. So we have our picture. We have from the table 11.345. Where is our chi-squared? Where? So that's a little misleading because they're both called chi-squared. But where is our test statistic? That's a better question. The test statistic is 4.8. This is a right-tailed test. This is not in our reject region. We are going to fail to reject. So we fail to reject because, cross that out, the test statistic is not in the critical region or the reject region. So we cannot reject this. We're going to fail to reject this null hypothesis. So there is not sufficient evidence. I cannot reject the null, so therefore I cannot support the claim. There's not sufficient evidence to support the claim. Are you noticing a theme to these conclusions, how they're very similar to chapter 9? Not sufficient evidence to support the claim that the births do not have uniform distribution. Now, I know there's some English majors out there that are like, how many knots are we going to put in one sentence? Can't we just say there is sufficient evidence to support the claim that the births do have uniform? And the answer is no. And the reason is, I think I said this before in a previous video, but the reason is we can't say OJ is innocent. He was found not guilty. Legally being found not guilty and him not doing it, totally different things. So we can't reject, can't support the claim. It doesn't mean the null hypothesis is true. It just means I can't throw it away. I don't have enough evidence to reject it. So we're kind of in, whenever we fail to reject, we're kind of in this limbo. So it's best to just not think, don't overthink this, don't get in this double negative spiral of confusion. Focus on what is always the same. There either is, let me get a good color here. There either is or is not sufficient evidence, depending on if we're going to reject or fail to reject. And then the claim is always the alternative. Just stick with that pattern. We established it in chapter 9. And even though we are doing the goodness of fit test instead of test, it's just using pictures off to the side. That must mean it is time for this video to end. So let this sink in. There will be another video with more practice, but this is all the new stuff for chapter 11. So we'll have more practice on this, but there will be nothing new or added to this test. All right, I'll see you in the next